So, in the last few videos, we learned about optimizers. We learned about the different kinds of gradient descent. We came across the term momentum. And we learned about some rather new optimizers like AdaGrad, AdaDelta, and Adam. Today we will discuss something known as weight initializers. So what exactly is weight initializers? If you remember, this is the structure of a MLP, multi-layer perceptron, and whenever we assign weights, what I mentioned was these weights were randomly assigned. Now this statement is partially true. So what that means is it is randomly assigned, yes, but it is randomly assigned from a distribution. So all the weights will lie in some sort of a distribution, let's say a normal distribution or a uniform distribution or something of that sort, right? So all these weights are randomly assigned but from a distribution. So why is that important? First, let us talk about some of the other things. So we know that weights should neither be too small and not too big. So why is that? Let us go back to this problem. So we have the loss here which is against the weights. So what I mentioned is if we go very slowly, our weights are not getting updated a lot and it will take a very long time to converge, or maybe we might not even reach here. So what I mentioned is if the differentiation is very small, our weights will not get updated, and this problem statement was known as the vanishing gradient problem. That means the gradient vanishes or becomes zero, as the name suggests. So this happens if the weights are too small. Other thing, what happens when the weights are too big? We come across the problem of gradient explosion or exploding gradient, just the opposite of vanishing gradient. So you can understand in this scenario what happens is this differentiation becomes very large, very large. So if this is very large, what will happen is the update will become very haphazard. So let's say we are here, so we'll go down a very big step. The next turn we'll take again a very big step. Okay, and suppose we realize we have come forward a bit, so we want to go back, but since the steps are very big, we'll again go back this whole big time. So this problem is known as the exploding gradient problem, and this happens when the weights are too big. So we need to somehow clip these weights. Clip as in we need to keep them intact so that they do not cross a particular range, right? So for that we need a distribution. Hence we have to use the weights from a distribution. So what sort of distributions should we use? Okay, there is another thing though. Yes, we know that the weights should not be too big or too small. The second thing is the weights should not be equal. So why is that? Let us look in the problem statement. If all these weights are equal, let's say 2, 2, 2, their updates will be equal. If their updates are equal, the new weights are equal. Hence, there is no somehow defining which input should be given more weightage compared to the other input. Hence, we should make sure that the weights are neither too big nor too small, first point, and second point, that the weights are not equal. So, they should be randomized, but randomized from a distribution. Okay, now before I explain how the weights are initialized, let me come across a few concepts here. So let's say this is a neuron. It has 3 inputs and 2 outputs. So we have a term called fan in. Fan in is equal to the number of inputs. So here 3, and fan out is equal to the number of outputs, that is 2. So if we have like say 4 inputs and 3 outputs, so fan in will become 4 and fan out will become 3. Nice. Okay, so these are the few concepts that you need to know, not very difficult. So now let us move on to some of the initializations. So the first initialization is basic from a normal initialization. So all the weights of this format will be initialized from a normal initialization which lies between 0 to sigma. Right, this is very basic. Now it is very important that we have a center at 0 so that we give enough weightage to even negative weights. So that means this is not at all related in any way to the output that we are getting. So that is also very important. So that is why a normal distribution. Second, from a uniform distribution. So the weights will be initialized from a uniform distribution which lies between minus 1 by under root of fan in to 1 by under root of fan in. Here it totally depends upon the input. So if suppose your fan in is, let's say, 4, so you have minus 4 here and plus 4 here, your distribution will look like this. This is a uniform distribution, right? Okay, so the next thing that we have is Xavier or Gouraud initialization. So these both are the same names of the scientist, and they again have two types of different initializations. So the first, let us look into the normal initialization, where weight Wkij lies for normal distribution which lies from 0 to sigma, and sigma is 2 by fan in plus fan out. Now this is the first time that both the number of inputs and outputs has been taken into consideration. So this is a Xavier or Gouraud initialization for normal distribution. So this is for normal distribution. Okay. The next one is the weights are randomly initialized from a uniform distribution which lies between minus under root of 6 by under root of fan in plus fan out plus under root of 6 by under root of fan in plus fan out. Now this is for a uniform distribution. So you have Xavier and Gouraud initialization. The next type of initialization that we have is Hay initialization. So this is named after the researcher who came up with this initialization. So again, this is of two types. We have a normal one and we have a uniform one. So here what he says is the weights are randomly from a normal distribution which lies between 0 to sigma. Here sigma is equal to under root of 2 by fan in. And the second one, that is for the uniform initialization, we have the weights come from a uniform which lies between minus under root of 6 by fan in to plus under root of 6 by fan out. So again, this is for normal initialization and this is for uniform initialization. Now this normal and uniform totally depends on what type of data you are using. So Hay initialization is usually used with activation functions like ReLU, leaky ReLU or any other type of ReLU. And Xavier or Gouraud initialization is usually used for sigmoid activation. So yes, that is it. Let us just recap. We have weight initializations, and the two most important things to make sure of while having weight initializations is that the weights are neither too big or too small, because we can have the problem of vanishing gradient or exploding gradient, and that the weights must not be equal. Then we came across two concepts, fan in and fan out. Fan in is equal to the number of inputs that are being put into the neuron, and fan out is the number of outputs that we are getting. Then we have different types of weight initializations. We have normal initialization, uniform initialization, and we have Xavier or Clairaut initialization and Hay initialization. So Xavier and Clairaut initialization is usually used for sigmoid activation functions, and Hay initialization is usually used for any type of ReLU kind of functions, activation functions. So in the next class we will learn a few more other things.
So that's it. Thank you for watching the video and keep learning.